Yes, it is possible to use a single, larger transformer and derate it for multiple loads. The National Electrical Code, specifically Section 450.4a3, addresses this possibility. While the NEC does not explicitly provide a derating formula, a commonly used and accepted approach involves applying a derating factor. The formula generally used is derated transformer capacity equals total load capacity divided by the number of transformers multiplied by 0.8. In this formula, total load capacity represents the sum of the load capacities of all connected loads. Number of transformers signifies the quantity of transformers being used to supply the loads. The 0.8 represents the derating factor, which is equivalent to 80%. To effectively apply this formula, firstly, calculate the total load capacity of all equipment that will be connected, such as the computer equipment, lighting, and the heat pump. Secondly, determine the number of transformers to be used, which in this case is 1. Thirdly, apply the derating formula. The derated transformer capacity will equal the total load capacity divided by 1 multiplied by 0.8. For instance, let's consider an example where the total load capacity is 100 kVA. Applying the formula, the calculation would be derated transformer capacity equals 100 kVA divided by 1 multiplied by 0.8. The result is 80 kVA. Therefore, in this scenario, a single 80 kVA transformer could be used to supply the computer equipment, lighting, and the heat pump. There are several benefits to derating a transformer. One benefit includes cost savings, because using a single larger transformer can be more cost-effective than using multiple smaller transformers. Another benefit includes reduced space requirements, because a single larger transformer occupies less space than multiple smaller transformers. A further benefit includes improved efficiency, because a larger transformer typically operates with higher efficiency than smaller transformers. It's important to note that the derating factor of 0.8 is predicated on the assumption that the transformers are operating at or below their nameplate rating. If the transformers are subjected to overloading, the derating factor may need to be adjusted accordingly to ensure safe and reliable operation. It is always recommended to consult with a qualified electrical engineer. Their expertise will verify the suitability of a derated transformer for the specific application, ensuring compliance with all relevant codes and standards while maintaining safety and performance. Factors to consider when determining whether to use one larger derated transformer or multiple smaller transformers extend beyond the basic calculations. It involves a comprehensive understanding of the load characteristics, operating conditions, and potential future expansion. A qualified electrical engineer can assess these factors and provide tailored recommendations. Load characteristics play a significant role because different types of loads exhibit varying demands on the transformer. Linear loads, such as incandescent lighting and resistive heating, draw current in a sinusoidal waveform that closely matches the voltage waveform. Nonlinear loads, on the other hand, such as electronic devices with switching power supplies, draw current in short, sharp pulses that distort the voltage waveform. These harmonic currents can lead to overheating and reduce transformer lifespan. When dealing with nonlinear loads, it's crucial to select a transformer specifically designed to handle harmonic currents. These transformers typically have a K-factor rating that indicates their ability to withstand harmonic heating effects. Derating the transformer may also be necessary to compensate for the additional heating caused by harmonic currents. Operating conditions also influence the selection process. Ambient temperature, altitude, and ventilation all impact the transformer's ability to dissipate heat. High ambient temperatures, high altitudes, and poor ventilation can reduce the transformer's effective capacity, necessitating further derating. The NEC provides guidelines for derating transformers based on ambient temperature in Table 450.3. Altitude derating may also be required in accordance with manufacturers' recommendations. Potential future expansion is an often overlooked aspect. If there's a possibility of adding more loads in the future, it's prudent to select a transformer with sufficient capacity to accommodate the anticipated growth. This avoids the need to replace the transformer prematurely, saving both time and money. When considering a single larger transformer versus multiple smaller transformers, factors such as redundancy and maintenance should also be evaluated. Multiple smaller transformers offer redundancy, meaning that if one transformer fails, the remaining transformers can continue to supply power to the critical loads. This can be crucial in applications where downtime is unacceptable. Maintenance is another factor to consider. Multiple smaller transformers may be easier to maintain and repair than a single larger transformer. The decision ultimately depends on the specific application and the priorities of the facility owner. The NEC provides specific guidance on transformer installation, protection, and grounding. Section 450 covers transformer installation requirements, including clearances, ventilation, and fire protection. Overcurrent protection is addressed in Section 450.3, which specifies the size and type of overcurrent devices required to protect the transformer from overload and short circuits. Grounding requirements are covered in Section 450.5, which mandates that transformers be properly grounded to minimize the risk of electric shock. In addition to the NEC, other standards and guidelines may apply to transformer installations. The National Electrical Manufacturers Association, or NEMA, publishes standards for transformer construction and performance. The Institute of Electrical and Electronics Engineers, or IEE, develops standards for transformer testing and application. Consulting these standards can provide valuable insights into best practices for transformer selection, installation, and operation. In summary, using a single larger derated transformer can be a viable option for supplying multiple loads, but it requires careful consideration of various factors, including load characteristics, operating conditions, future expansion, redundancy, maintenance, and applicable codes and standards. Consulting with a qualified electrical engineer is essential to ensure safe, reliable, and efficient installation. The engineer will assess the specific needs of the application, perform detailed calculations, and provide recommendations tailored to the situation. This ensures that the transformer is properly sized, protected, and grounded, and that it meets all applicable requirements. When determining the derating factor, consider that while 0.8 is a common value, it may not be suitable for all applications. The appropriate derating factor depends on several factors, including the transformer's design, the load characteristics, and the operating environment. Some transformers are designed to operate at higher temperatures than others, and these transformers may be able to handle higher loads without requiring significant derating. Similarly, if the load is relatively constant and predictable, a smaller derating factor may be acceptable. However, if the load is highly variable or includes significant harmonic content, a larger derating factor may be necessary. The operating environment also plays a role. High ambient temperatures or poor ventilation can reduce the transformer's ability to dissipate heat, necessitating a larger derating factor. The transformer manufacturer's datasheets provide valuable information about the transformer's thermal characteristics and recommended derating factors for various operating conditions. It's crucial to consult these datasheets and follow the manufacturer's recommendations to ensure proper transformer operation. In addition to the derating factor, other factors that influence transformer sizing include voltage regulation and inrush current. Voltage regulation refers to the transformer's ability to maintain a stable output voltage under varying load conditions. A transformer with poor voltage regulation may experience significant voltage drops when subjected to heavy loads, which can affect the performance of sensitive electronic equipment. To minimize voltage drops, it's essential to select a transformer with adequate capacity and low impedance. Inrush current is the high current that flows into a transformer when it's initially energized. This current can be several times higher than the transformer's normal operating current and can cause nuisance tripping of overcurrent devices. To mitigate inrush current problems, it's common to use slow-blow fuses or circuit breakers with high magnetic trip settings. Alternatively, special inrush current limiting devices can be installed. Transformer efficiency is another important consideration. Transformers are not perfectly efficient, and they consume a certain amount of energy in the form of core losses and copper losses. Core losses are caused by the magnetization and demagnetization of the transformer core, while copper losses are caused by the flow of current through the transformer windings. These losses generate heat, which must be dissipated to prevent overheating. High-efficiency transformers are designed to minimize these losses, which can result in significant energy savings over the transformer's lifespan. When selecting a transformer, it's essential to consider its efficiency rating and choose a model that meets the specific energy efficiency requirements of the application. The Department of Energy, or DOE, has established minimum energy efficiency standards for transformers, and many utilities offer rebates for the purchase of high-efficiency models. Transformer protection is also a critical aspect of transformer installation. Transformers must be protected against overload, short circuits, and other faults to prevent damage and ensure safety. Overcurrent protection is typically provided by fuses or circuit breakers, which are sized to protect the transformer windings from excessive current. Ground fault protection is also essential to detect and interrupt ground faults, which can pose a serious shock hazard. Ground fault protection is typically provided by ground fault circuit interrupters, or GFCIs, or ground fault relays. Surge protection is also important to protect transformers from voltage surges caused by lightning strikes or switching transients. Surge protection devices, or SPDs, are installed to divert these surges away from the transformer, preventing damage to the windings and other components. Transformer maintenance is often overlooked, but it's essential to ensure reliable and efficient operation. Regular inspections should be performed to check for signs of overheating, oil leaks, or other problems. The transformer winding should be tested periodically to check for insulation breakdown. The cooling fan should be cleaned regularly to ensure adequate ventilation. In addition to these routine maintenance tasks, it's also important to keep accurate records of transformer performance, including voltage, current, temperature, and oil level. These records can be used to track the transformer's condition and identify potential problems before they become serious. Remember that using a single larger derated transformer instead of multiple smaller transformers can offer cost savings, space savings, and improved efficiency, but it requires careful consideration of various factors. Consulting with a qualified electrical engineer is essential to ensure a safe, reliable, and efficient installation. The engineer will assess the specific needs of the application, perform detailed calculations, and provide recommendations tailored to the situation. This ensures that the transformer is properly sized, protected, and grounded, and that it meets all applicable requirements. Considering NEC Table 310.15, B1 for allowable ampacities of insulated conductors rated up to and including 2000 volts, it provides guidance on adjusting ampacities based on ambient temperature and the number of conductors in a raceway or cable. The table helps in determining the appropriate conductor size to ensure it can safely carry the intended load current without exceeding its temperature rating. For example, if the ambient temperature is higher than 30 degrees Celsius, a correction factor is applied to reduce the allowable ampacity. Similarly, if multiple current-carrying conductors are bundled together, a derating factor is applied to account for the increased heat generated. These adjustments are crucial for maintaining the integrity and safety of the electrical system. Also, consult the NEC for grounding electrode conductor sizing, specifically Table 250.66. This table is used to determine the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor connects the service equipment to the grounding electrode system, providing a path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices. Proper sizing of the grounding electrode conductor is essential for ensuring effective grounding and minimizing the risk of electrical shock. Lastly, it's important to refer to NEC Article 220 for load calculations, which provides detailed instructions on how to calculate the electrical loads for various types of occupances. Accurate load calculations are essential for determining the appropriate size of service equipment, feeders, and branch circuits. Article 220 covers various aspects of load calculations, including general lighting loads, receptacle loads, appliance loads, motor loads, and air conditioning loads. It also provides guidance on demand factors, which allow for the reduction of calculated loads based on the assumption that not all loads will be operating simultaneously.